Hi, and welcome back to your next video, specifically on exponential decay and 7.2 from your book. Before we get started on 7.2, I first want to recover a little bit of a few things that we have talked about in the past couple days in 7.1. First, the biggest idea that I want you to take away from the first two sections, the last one we just went through and the one that we're going to go through today, is the idea that every one of these exponential growth or exponential decay that you're going to find today is rooting from the same kind of equation. And the one equation that you're going to see in the top right hand corner of your screen right now is the idea of y equals ab to the x. Okay, this is the exponential function where b is going to be that base, and sometimes we're going to call it the growth factor if we're talking about a growth model, as well as today you're going to see also that representing a decay factor, something that's getting smaller and smaller and smaller. We know a already to be a multiplier, something out front that multiplies that model, that growth exponential function in one direction or the other, in terms of making it much, much larger by having a number bigger than 1, as well as a number being less than 1. And again, I'm talking about a in that case. So again, understand that there's a bigger picture here, and we have an exponential function, and an exponential function in general looks like y equals a b to the x. But then the last 2 days we've talked about two specific kinds of models. From that, we've talked about this exponential growth model, and the exponential growth model is y equals a times 1 plus r to the t. When I look at something like this, okay, I'm talking about some kind of growth model. What is my rate that I'm increasing by? So if you're to compare these two models, you're going to see first that a stay the same. Okay, that multiplier, that amount out front stays exactly the same. Okay, realistically, the only thing that is changing from the generic model of the exponential function to get to the exponential growth model is the idea that 1 plus r has now replaced b. Okay, and that makes sense because if I say that b is the base, that's a growth factor in this case, okay, I want something bigger than 1. If my r is my rate that you learned yesterday, if r is my rate of increase, I'm increasing by 5%, I'm increasing by 25%, whatever it is, if I add 25% as a decimal to 1, I get 1.25, therefore b bigger than 1. And we noticed from yesterday that if that number is bigger than 1, I develop an exponential growth model that it gets bigger and bigger and bigger graphically as I move further and further and further to the right on the x-axis. And again, the x just gets swapped out for the t because now we're talking about some specific model where we have a time factor. You know, how long is this growing for? Is it growing for 10 years? Is it growing for 15 years? Whatever it might be. So we've gone away from the generic x, and now we've actually labeled that axis to be t for a time factor. So if you look at this, again, we've kind of named that a to be that initial amount. And then we have also talked about this r being the rate of increase. In this case, it's may increase. You're going to find that to be the rate of decrease as well if we talk about a decay model that we're going to talk about today. And then t is time. T is going to be something that we talk about years. We can talk about hours. We can talk about seconds. Generally, we're talking about years, but that can change from model to model. But in general, these are the three variables that you're going to have in an exponential growth model. And then right at the end of the lesson yesterday, we talked about some kind of compound interest. Okay, and the most applicable kind of model is the idea of a bank account, and we have some money in there, we have an initial amount in there, and they say the bank's going to say, hey, you're going to earn this % on that every single year. Okay, the only difference is instead of doing it every single year and only doing it once a year, okay, you could do it multiple times a year. You can do it weekly, you can do it monthly, and so we have to account for how many times they're compounding, actually taking that action, taking what's in the bank account and actually finding how much of that % goes back into your bank account, and then going ahead and accruing more and more and more money depending upon how often you do that compounding. And so we talked about this. We talked about the fact that now this model of this exponential growth model of y equals a times 1 plus r to the t now changes a little bit. Now we have a equals p times 1 plus r over n to the nt. Again, you can see that the basic stays the same. Okay, from the first equation, the second equation, the third equation, that initial amount hasn't changed. We called it A in the first two, and now we call it P because now in a bank account situation, we're still talking about the idea of a principal. Okay, and the principal is how much money is still in your account. Okay, the big A now becomes the amount that you have after you do this process. So this is really what I like to call the amount after t years. So what is my amount after you do all this compounding? Okay, what happens when, well, how much is left in your account, or how much has been gained into your account at the very end? What's your new amount after the compound has happened? Okay, the R stays the same, so there's nothing new there. Okay, my rate stays the same, that's still R. Okay, but now you can see that now I have to account for how many times I'm actually increasing that rate, or how many times am I compounding with that rate. Okay, and that's what the N is a new piece of this puzzle here. And if you look at N in both cases, okay, really what I like to say is this is the number of times, so I'll try and abbreviate here, is the number of times we are using R, okay, or how many times we compound R, and I'll say R each year. Okay, when you look at that, we want to say, hey, if I'm compounding annually, that N is 1. And think about what that means. If that N was 1, it would be R over 1 inside the parentheses, which is really just 1 over R. And if it was 1 times t in the top, we're really back to the second equation. We're back at the exponential growth model where it happens once a year. Okay, in this one, we're just accounting for the fact that it could happen more times a year. It could happen monthly, it could happen daily, it could happen bi-weekly. Whatever it is, we're going to account for that now by adding that extra variable in there of that N factor of how many times you're compounding each year based on the number they give us that we talked about yesterday of monthly, daily, or whatever it may be. So these are 3 models. Yeah, I do expect that you would know this. This is the general model at the very top. Number 1 would be something I would expect you to be able to graph all the kind of generic models of an exponential function. Okay, number 2, certainly if I give you some sort of model that we're not compounding, we're just going to go ahead and talk about exponential growth models that apply to a certain situation where I'm compounding only really once a year. Okay, we can go ahead and use the exponential growth model. And then finally, the actual compound interest. A equals P times the quantity 1 plus R over N, all to the NT. Okay, that's certainly something that's very important if we're compounding or using that interest multiple times a year. All 3 will be something I expect that you know going forward. Let's do a one. Here's a problem. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% a year. So in number 1, it says, I want to write an exponential growth model giving the number n of incidents t years after 1996. Okay, so right away it tells me, hey, I want, and I'm going to put a little box around it, I want to do an exponential growth model. So of the 3 that we have, if I put the generic name, or if I put the generic model up there, my generic model is y equals a times 1 plus r to the t. That's the exponential growth model if you were to go back in the video and take a look. Okay, but now we need to identify all our amounts that we have. Okay, I want to write an exponential function, so I'm going to actually make a function, so I want to leave 2 variables in there. Okay, it says I want to know that giving the number of incidents after t years. So the instance is going to be the output depending upon how many years I've gone into this process. So I think that n is going to be replaced with, or y is going to be replaced with n, so n equals. It's still going to be t in there because I want to talk about how many years after, so t is going to remain. So there's my 2 variables, n, and eventually I'll put t at the very end. But now I got to figure out what a is. What is my a amount? I'm going to kind of keep a log over here on the side. I'm going to see if green works here. Okay, I think green is pretty clear there. Okay, what's my a is my initial amount. Okay, well in 1996 when I started tracking this, or when it started trending, okay, I think I started the first few words of the problem says I started with 2,573 incidents that I started with. Okay, and then I also, it looks like from my model, I need my rate. How often is this happening? What's the consistency of how many incidents am I having a year? And it looks like, according to the last sentence in the problem, I have about 92%. So my rate, again, I need it as a decimal, so 92 would be 0.92 as my percent as a decimal. And I think I have the things I need to go ahead and plug it in. So if I go back to my formula here, right in the middle of the screen, I have n equals my initial amount of 2,573 times 1 plus my rate, which is 0.92, all raised to the t value. Now you're more than welcome to leave it like this, but there is something easy to simplify, and what's easy to simplify is the 1 plus 0.92. You might as well go ahead and do that. It's an easy calculation. So I think I have n equals 2,573 times the quantity 1.92 to the t. Now get out of your head right away that you can think you can multiply the 2,573 times the 1.92, because remember your order of operations. Exponents come before multiplication. So realistically, the 1.92 is locked in by the exponent, and so I can't multiply those two numbers together until I get the exponent out of the way. And so because of that, that's the best I can do. It's the most simplified I can get. I think this in the middle of my screen right here is going to be my exponential growth model. If I have that, I think I can answer number 2. Number 2 says, how many incidents were there in 2003? Okay, well, there's a little bit of side work to be done. We know in 1996, I would consider that to be t equals 0. So if I want to know 2003, I think what I want to do is go ahead and say, well, 2003, how many years later is that? Okay, you can either say, okay, 2003, and you can actually subtract 1996, because 1996 is your 0 year. I think 2003 is 7 years later. So if I look at that, I think I have my t-value, and if I want my t-value, I think I can solve the problem. The number of incidents is n equals my model, 2,573, times my growth factor, which is 1.92. I know it's growth because that number, that base, is bigger than 1. And I want to raise it to my t-value, so in this case I want to do 2003, which is equivalent to when the t is 7 years down the road. And go ahead and plug in your calculator. I'll do the same thing. If I do 2,573 times a quantity 1.92 to the 7th, I think I have a number of incidents in 2003 to be 247,480, and if I go ahead and round to the nearest decimal, 485. Okay, what we're going to talk about today is exponential decay. So all of us know what decay means. Decay means something's getting smaller and smaller and smaller. Something's getting whittled away. And so when we talk about growth, it's getting bigger and bigger and bigger. If you think about that idea of the graph, as you move left or right for a growth, it's getting bigger and bigger and bigger and bigger. And so instead, on a decay, we're doing exactly the opposite. So when you look at this, there's a lot on the screen. So feel free at any point to pause it, look at it, and write down anything you need to do, whatever you feel is most comfortable. Okay, we showed this exact same kind of look, okay, but it was for growth a couple days ago. For growth, we talked about this B factor, that base, having to be bigger than 1. And we noticed that in the last couple problems. If that base number, and I'll locate it right here, if I look at the function in the first sentence right here, if that B, that base, is bigger than 1, I'm going to have growth as I move left or right. Okay, but as you can see here, if I have a B value, that is a fractional value. So if I look at this, if I have 0 is between, or B is between 0 and 1, now all of a sudden I've created a situation where I've created something that we call a decay function. Okay, so if you look at this, this is kind of the idea of what a decay function looks like. Here's something nice. You should see this, and that should be a nice indicator for you. Okay, even though it's a decay, both decay and decay and growth functions both go through 0, 1 as long as you haven't messed with it in terms of multipliers or add, subtract, moving it up and down and transforming it like we've done. Okay, there's a kind of a nice indicator again that we start at 0, 1. But you can see here, as I move further and further and further and right, as I approach infinity for my x-axis, for my inputs, it's getting closer and closer and closer and closer to 0, just like if I were to sketch out the power function up in the top right corner. Okay, this was my idea of the power function, or excuse me, the growth function. You saw that the exact opposite way, okay, where I was going approaching negative infinity as I was moving further and further and further this way. Okay, now all of a sudden I was going and approaching negative infinity. This one's just the flip. And so the only thing that really causes that, again, if you look in the top left, it's underlined in red. Okay, what's causing that is that B is in between 0 and 1. If that's the case, then we've created a sort of decay function. And at the very bottom, it's always good to go and kind of go over that and make sure you're seeing it. Domain is your input. Okay, your range is your output. If I look at my domain here, I think I'm going to hit every single x value. As I move further and further to the left, I think it's going to go off into infinity and hit every single value, as well as, even though it's getting closer and closer and closer to 0 on the right, as it approaches positive infinity, it's still going to hit every single x value. Okay, that's different for the range. The range is going to get infinitely close to 0, but it's never going to get down here in the negative anywhere. It's never going to get down there. It's going to get close to 0, but it's never actually going to hit 0. So my range is everything greater than 0 as a result. Okay, there's definitely a restriction on my range here when I do these type of problems. So, like 7-1, day 1, let's graph a couple. Okay, the first thing I want to do, and I'll try and go ahead and color code these, I think that's a little bit easier. I want to do g of x first. So again, have your calculator handy, and I want to plug this thing in. So if I want to do g of x, obviously we can make a nice little table if we wanted to. So here's x, y, and I'm going to go ahead and plug in a few values in. You know that we did this last time where we plugged a little bit on either side, so I'll put 0 in the middle. When I plug 0 in the middle, I think 2 to the 0 power. I think we might even done this one. 2 to the 0 is definitely 1. So I'll plug that in and graph it. And if I go a little bit further to the right, if I plug in 1 or if I plug in 2, if I plug in 1, that's really 2 to the first power or 2. If I plug in 2 squared, I think I get 4. The other way, if I plug in -1, that's really 2 to the -1. Again, negative exponents does not mean negative value. It means you flip it over the other side. So this right here really means 1 over 2 to the 1, or simply 1/2. And again, with -2, that means 2 to the -2. And when you plug that in and simplify it, I think we get 1/4. So let's go ahead and graph those. I have 0, 1, I have 1, 2, and I have 2, and I have 4 way up here. I think I have a pretty good idea of what it's looking like on this side. And even if I put in 3, I think when it's 2 cubed, I think I'm way over here at 8. So I even get one more that I couldn't fit in my table. And on the other side, it's getting closer and closer and closer to 0. You can see it went from 1. If I plug in -1, I get 1/2. If I plug in 2, I get 1/4. It's just getting infinitely closer to 0 on the left side. Again, this is a growth function. Why? Because the number, that base, that 2, is bigger than 1. Okay, but then what if I go ahead and switch it up a little bit? What if I go ahead and do f of x instead? So first let me label this. This was g of x, so g of x was equal to 2x. It's always good to label your functions, especially if you're going to graph multiple at a time. What if I want to graph f? So if I want to graph f, and again, it might be helpful for you to have a calculator here, I'm going to go ahead and make another table. Okay, so if I make an xy table over here on the left side instead, okay, I'm going to do exactly the same thing. Put 0 in the middle. If I plug 0 in the middle, let's plug a few things in. For example, if I plug in 1, okay, that really means it is 1/2 to the first power. When I do 1/2 to the first power, I think that's just 1/2. If I plug in 2, I think that is really 1/2 to squared. And when I do that, I get 1/4. Hopefully you're noticing already that the further and further to the right I'm going, almost looks like the power function, the growth function on the other side, as it was getting closer and closer to the left. So it's almost like it's mirroring. So if I plug this in, if I plug in 0, for example, plug in 0, 1/2 to the 0 is still only 1. And so when I plug in just those, you can see already what's happening. I plug in 1, when I plug in 1, I get 1/2. When I plug in 2, I get 1/4. I'm already getting that reciprocal, or kind of that symmetrical look, okay, that the 2 of x has if I flipped it over the y-axis. So I bet you if you anticipate, if I were to plug in -1, I think that this one may go ahead and reflect over. Let's check it out. I know it's kind of hard to see, but if I plug in -1 there, you're always more than welcome to plug in your calculator. When I'll go ahead and do 1/2 all raised to the -1 power, I think I get 2. And all of a sudden, we're on to some kind of pattern. So -1 up to 2, and I'm guessing that then this one over here, and again I'm on the graph here, so when it's up at 2 and over up at 4, I think I'm going to be at -2, I'm going to be at +4. If I'm over at 3 and up at 8 on the growth function, if I'm over at -3, I bet I get out -8. And all of a sudden, it starts to mirror. But you can see this has to be a decay model. And so this one right here, this f of x, is definitely a decay model, because as it moves left to right, it's getting infinitely closer to 0. It's getting smaller and smaller and smaller, versus the growth function, which is in blue, that's getting bigger and bigger and bigger as your x values get larger, as you move down your domain and further to the right on the graph as you read it left to right. So let's try a little bit different one. Let's try a little bit harder one. Let's try 2/3. Okay, I'm going to move my graph over here a little bit, so I go ahead and make sure we have enough room for everything that we need. We're going to try and group a couple things together here. That would be probably a little bit more beneficial, so we can keep everything going at the same time. So I'm going to go ahead and move this over. That way we have a little bit of open space to go ahead and build yourselves a table. Okay, when you start getting something like this, okay, when it gets to 2/3 x, when we have a fractional value as that base, okay, I will expect certainly that we can do some of this by hand, okay, but for the most part, when these fractions get pretty hard, I want to expect that you try and do a lot of this on your own. And so go ahead and have a calculator handy. We can plug it in and see what we get. So for example, this one should be the one without a calculator. When I go ahead and plug 0 into 2/3 x, that is 2/3 raised to the 0 power, and when I do that, I get 1. Again, that's that nice starting point for these parent functions. So I'm going to go over and graph it. Okay, pretty typical, pretty expected at this point. That's going to go through 0, 1. Okay, now if I plug in 1, if I plug in 1 of that power, I think I get 2/3. Again, you should notice already from 1 to 2/3, it's already getting smaller. So I would anticipate that this, when I plug in 2, it's even smaller and smaller and smaller. Go ahead and take out your calculator, and when you do, okay, you can go ahead and do 2/3 raised to the 2nd power, which is really 0.444 repeat, but that also is 4/9. And I know that because if I do 2/3 squared, we know that we can distribute that power to both the 2 and the 3, and when I do that, I get 4/9 as a result. Okay, I can do that. I can distribute the power when there's only multiplication and division on the inside. Go the other way. If I plug in -1 and I plug in -2, if I plug in -1, when I plug in 2/3 raised to the -1 power, okay, I think I get 1.5. And when I plug in 2/3 raised to the -2, I get 2.25. And again, just to ensure that you and I are on the same page, I'm going to bring up my calculator again to make sure that you're seeing the same thing I am. And so I am going to grab my calculator, which is behind. Clear that out and make sure we can actually type that in. So if I bring my calculator a little bit over here and kind of get off my smart ink here a little bit, clear the screen so I'm not writing all over the screen instead of using the select button. Clear the ink. Let's take a look. So if I want to plug in 2/3, 2 divided by 3, all raised to the -2. Notice I'm grouping the -2 inside. Again, that's really important for you guys that hold an 83 in your hand right now. And when you get that, you get 2.25. So make sure you're copying that behavior here in the calculator to make sure you're getting the same thing I am. So let's go back. Let's graph this. If I look at this, I think I go ahead and if I go to left first, -1, I'm up at 1.5. I'm at -2, I'm up at 2.25. You know, not great numbers, but at least I'm getting an idea of what's going on. And 1, 2/3, and then 2, even 4/9, which is just kind of right here, close enough. And you can see here that I'm kind of creating a nice, almost a lot more gradual looking graph versus the one that was sharp. Okay. Now, what if I do this? I'm not going to graph this. I'm not going to take the time to graph this because I'm going to have you do it on your own. You're going to pause the video here in a second. You're going to do it. Okay, but tell me what's going to happen here. We know enough about parent functions at this point that if I go ahead and group all this stuff together to make sure I can move it all together, you got to ask yourself, I'm going to undo that. Sorry, folks. If I look at this function, do you see something that's in common from the previous slide? And more specifically, if you go back to the previous slide, which I'm going to, okay, do you agree that it's the same parent function of 2/3 of the x, the same base and the same power of x? Okay, realistically, if I were to circle what I already know, I already have this 2/3 x idea, and I already have it graphed. Okay, and we know parent functions enough to know what every little piece of this is going to do. It's just a matter of going ahead and recalculating to actually make sure that our beliefs are the same. If I don't worry about the 3 out front, if I don't worry about the multiplier up front, we should know exactly what this means. Okay, this +1, if I talk about that +1 right there, it's on the inside of the function. If it's on the inside of the function, it's move left or right. It's opposite than what we think, and so it's going to move left 1. And then if I look at this, if I have -2, I think that comes down, and that's going to move it down 2 because it's on the outside. And I know if it's on the outside, it moves up or down. It's true to what you think. And the 3 is just a multiplier. We're going to take whatever that is, we're going to multiply it by 3, and so we're really going to make the thing bigger because we're multiplying by 3. So take a minute, pause, okay, and go ahead and see what you can do. Okay, as I do this and graph it in, you can see that it's getting closer and closer and closer and closer and closer and closer and closer to -2, but never actually crossing it, which makes sense Because we know from the parent function, if I go back to our very first parent function, you can see that this graph is getting infinitely closer. There's an asymptote. You can see that dotted line I'm putting here. There's an asymptote right at really y equals 0, the x-axis. And so you got to ask yourself, if I go to my problem that we just did, which is this one right here, why is that changed? Well, we moved it down too. We moved our function down too. And so when we do that, it also moves my asymptote. So it moved off the x-axis and it moved down too. So again, here's my asymptote right here. It's getting infinitely closer to that, but it's never actually going to cross it. Finally, how does this actually apply to real life? So we have this decay model, and we talk about the idea that, hey, if that base number, if right above this, I put y equals ab to the x. At the very beginning of this lesson, I said, hey, if the b value is bigger than 1, I got a growth model. And now, what if I have a decay model? Well, it's logically, as we saw with our graphs, if that b value is something in between 0 and 1, or creating a fraction, now all of a sudden I have a decay model. And so where you had a growth model yesterday where you had a times 1 plus r to the t, you can see now in this situation I now have 1 minus r. So now the mindset changes. Instead of going ahead and gaining 7% or increasing 92% or whatever it is, now I'm going to be losing that same percentage. And so if I take 1 and I subtract a certain percentage, I think I'm going to result in some kind of something less than 1. So if I look at this b value, which has been replaced with 1 plus or 1 minus r, if I subtract r off, I've created something that's less than 1. If it's less than 1, it's going to be graphed like the decay model that we've seen in the last couple of slides. It's going to, as we move left to right on the graph, it's going to get less and less and less and closer and closer and closer to 0. So notice that almost everything else stays the same. Y is still the amount after a certain amount of years. We're going to call it T for years. Okay, and then A is still that initial amount. What did you start with? What kind of amount did you start with? Whether it be money or cost or some kind of chemical. Well, what's the initial amount of that did you have? The rate is still the rate. Still expressed as a decimal, and R is still the rate at which you're decreasing. And T is your time, and for at least for the time being, we'll keep our time in years. So let's do one here before we call it a day. It says a new car, something that hopefully you guys can relate to here. Okay, when you have the chance to go ahead and buy a new car, it's one of the worst investments you can make. And the reason I say that is not because it's not a good thing, it's a great thing to have a car, but when you drive it off the lot, you lose a lot of percentage of what the cost is. So if you drive it off the lot when you buy it and you try and turn around and turn it back in and get your money back, you are not getting nearly the cost of what you paid for it the second before you drove it off the lot. So take a look at this one for example. A new car costs $25,000. The value of the car decreases by 15% each year. So every single year it loses 15% of the value that it had from the previous year. So the number one says, hey, I want to write an exponential decay model giving the car's value, which is y, in dollars after t years. So again, if I write the generic model on the board, I have y equals my initial amount A times, we know it's a decay model. If it's a decay model, I'm going to do 1 minus r, all raised to the t. Well, now in this case, again, let's label some things. I'm going to go ahead and turn to green again, and I'm going to go ahead and write down all the variables that I know. I know my initial amount. My initial amount of my car was $25,000. And I also know my rate. My rate was decreasing by 15%. So 15% of the decimal, I think, is 0.15. And then I want to leave t in there because I want to write a generic model. I don't want us to do a specific time. So it says, hey, I want to leave y, which is my value, in terms of t, which is years. So if I plug in what I know, I think my model looks something like this. Y equals $25,000 times 1 minus the 15%, or 0.15, all raised to the t. Similar to the growth model, there's something to simplify in there, and it's the parentheses. I can go ahead and say my new model really is y equals 25,000, and 1 minus 0.15 I think is 85%, or 0.85 to the t. I think this is my model that describes this situation where I have a $25,000 car and it's decreasing by 15% each year. And even if I were to give you that, I would expect that you know that this is a decay model by just looking at that base value of the exponential. If you look at the base, it's less than 1, 0.85, and therefore I'm going to definitely know I have a decay model. So number 2 says, hey, what about a specific situation? Okay, I want to know what the approximate value of the car is after 4 years. So y is the value. We've already determined that in 1. Y is the value, so that's what I want to find. Y equals. My model is 25,000 times 0.85, usually the t, but I think they've actually identified what t is. I want to know 4 years later, how much is my car worth? If it's still, working and everything and there's no other factors involved, okay, I want to say, hey, what happens if it decreases by 15%? What happens after 4 years? So pick up your calculators to punch it in. 25,000 times 0.85, all raised to the 4th power. When I do that, only 4 years later, my car is only worth $13,050 and really 16 cents. See you tomorrow in class. Have a good night.